Okay. It's kind of for the weekend. When I came back yesterday, I saw that Gary had made another video on quantum mechanics that I had not seen. And it's all about a theory about why a photon would be emitted and when, when you change the magnetic field around an electron. The thing is, and I'm fine with that. I appreciate the bravery bringing out, a system like this, and I take it with a grain of salt. I don't think that I'm not going to make fun of Gary like he's trying to win a Nobel Prize with it. It's more like a science fiction book, science theory. It would obviously have to be fleshed out to be real science, if it could be fleshed out. And I think it's fair for him to speculate that and give us, well, look, maybe this kind of thing. Look how much more common sense it would be. But that's where it really fails. Because a time reset, nobody's ever seen anything like that. That would be pretty magical just because it doesn't have the word random in it. I mean, when does it happen? When does it decide to happen? And if it happens regularly, then you need to make it cohere with relativism, or else we can use it to find out what the clock of the universe is, which, according to relativity, you can't. There is no single clock of the universe. We all have our own clocks. But what I really want to talk about, because I think a lot of people mistake this, is they hear about quantum mechanics as involving randomness, because it's the thing that shows there's some probabilistic behavior. It's not classical randomness. That's a very important thing to realize. It doesn't behave like dice. But anyway, that's what the theory is famous for. But it's not about randomness. The theory doesn't, quantum mechanics doesn't always just add up to a lot of randomness. Obviously not. Look around you. It's quantum mechanics, not leading to just total chaotic randomness. And it's really clear why that is. And any scientist that's saying, quantum mechanics doesn't really affect the macroscopic scale, ask them why. Because it does affect it. It is there. But they're saying, oh, you don't really see the weird quantum effects. Why? Because when you add those up, they cancel out. Okay. But they don't totally cancel out. They're still there. It's like magnetism. I love to use cups for my example. This cup. It's made of magnets. And yet, if I put a piece of metal to it, it doesn't stick. If I put a magnet to it, it doesn't stick. And yet it's made of magnets. Magnets, everything around you is made of magnets. 100%. And yet how many magnets do you just find in the wild? Somebody has to make one, right? You don't find much magnetism in the wild. It's because the magnetic fields of all these tiny magnets cancel out. They cancel out on the macroscopic level. To get an actual magnet on the macroscopic level, you have to take all the tiny magnets and turn their little magnetic fields so they're all aligned. Then the whole thing acts like a magnet, because it doesn't cancel out. In the same way, quantum mechanics, usually this random cancels out. Okay? Usually it cancels out. But you can build a device where it doesn't necessarily cancel out. Now, why does quantum mechanics on a large level turn into something more like classical mechanics, where you can make these more classical statements, where you can measure P and V pretty accurately? Well, it's because of the statistical pattern. If there's a like a probability pattern, right, of where a photon is going to hit a screen, and it's, you don't know where, but it's, mostly going to be at this point, less at this point, none at this point, and so forth. As you fire these one at a time, when you see just 20 of them, it'll still look just random, like you were looking at 20 stars in the sky. But as you fill it out with 10,000, 20,000, 50 million, it'll start to fill in, like coloring in, that pattern. That is the description of the probability. However, it won't fill it in perfectly. And anytime you take 1,000,000 points and do that, and you take a different 1,000,000 points, photons, and do that and get 1,000,000 points, both of them will look like they're filling in the same pattern. But if you look at each and every point, the points will be in different locations. Okay. So that's why it's not truly determinist, even the pattern, because though the probabilistic pattern expresses itself, it's not deterministically so. It's a pattern that's like a template that's being filled in by these natural events. If you had an infinite number of those events, the pattern in principle would be filled in. Of course, you'll always have a finite number of events. It'll never actually be fully filled in. But at the macroscopic level, we don't look at the little dots. Okay, we look at the pattern. We don't look at the atoms in the apple, we look at the pattern that they make, and that pattern can be filled in through probability, since there's, trillions of particles in that system. Okay? So, thinking that quantum mechanics doesn't affect the macroscopic universe is just wrong. It's like thinking magnetism doesn't. Of course, quantum mechanics makes up everything, and therefore that includes us. And the way we see what we think of as determinism is because we're looking at patterns, and we didn't notice that there was no determinism until we looked at the patterns close enough to realize they're made of pointillization and never filled in exactly, always a unique fingerprint to how the events happen, even though they fill in the end and look like a fingerprint. It's always unique, even though you can recognize the same pattern. And this becomes an analysis of patterns, which the brain is actually pretty good at. And therefore, we function in a quantum universe, even with an element of probability. And let's call it probability, not randomness, since randomness implies a classical notion of randomness. And quantum, randomness works much differently. Specifically, if you had random factors in classical mechanics, there would be no conservation of energy. But in quantum mechanics, even though there is the randomness, there's still conservation of energy, which is strange and fortunate, right?